we want to take a look at y equals 2 sine of x. And when we're finished, we're going to kind of compare that and see what the difference between that graph and the original parent graph y equals 1 sine of x. We want to see what the differences are. So, real quick, what's the amplitude?
2.
Uh-oh, hold on, not ready.
2.
Thank you. The amplitude is the absolute value of 2, which is 2. The period is 2 pi over b, and b is still 1, so the period is still 2 pi. And these don't get bad until the period changes. When the period changes, things kind of get a little stressful. Then you build the graph, x, y. So we're going to build our table. Starting at 0, we're going to skip 3 slots, and we're going to end at our period of 2 pi. Go in by halves. And then we're going to evaluate. If I plug in 0, I have y equals 2 times the sine of 0. Well, what is the sine of 0? Guys, think it through in your head. That goes through the ordered pair 1 comma 0, so the sign is 0. So it's 2 times 0, so that is still 0. So, and guys, the nice thing about the trig graphs is every other one is 0, so I also know that this one has to be, and this one has to be.
Is that like for real true always?
That's for real true always for trig
Just
graphs.
saying.
Not, well, for sine and cosine.
Okay,
But
for
for
real
all
true
sines and
always.
cosines, every other value will be 0. So we don't have to worry too much about those.
Okay.
Okay.
When you find the other one, can't you take the opposite?
Yes, and that's the other thing you'll learn is that really you only have to do the first 2 each time, and once you do, you know the others. So that's nice. So it's really not that bad. And that's what I like about the way we designed this table. That's kind of the way I do it, why I do it that way. Okay, so now we'll say y equals 2 times the sine of pi over 2. Well, the sine of pi over 2 is, let's see, it goes through the point 0, 1. So that sine value is, so we have 2 times 1, which is 2. And then once you know that one, the other one will just be the opposite because it's going to go up above and then come back down. So this one would have to be, and if you don't believe me, you could go work that out. So it's very pattern oriented, so it's not difficult once you know enough about the patterns to do it. And to me, like graphing by hand is kind of silly, like whoever does that in the real world, so that's not what I care about. But the patterns are important, and so that's why that's the only reason really we spend so much time on this unit, is so you can understand the different patterns of the trig functions. I'll throw it on a graph, and instead of stopping at 1 and negative 1, I have to go up to 2 and negative 2. Okay, so I have the points 0, 0, pi over 2, comma 2, pi 0, 3 pi over 2, comma negative 2, about right there, and 2 pi 0. So here is one period of y equals 2 sine x. How does it look different from the previous one?
It's taller.
Yes, it's elongated. It's taller because the amplitude is more. There's more space. This right here is called, does that have a name? That midline of the wave?
The x-axis.
Well, it does here, but the
Wavelength.
yeah, no, I mean like the whole thing, like just the mid. Well, I always just call it the midline. Like the midline of the wave is like right here. And right now it's on the x-axis. It won't always be, is why I said that. And so that's how far it is. The amplitude is how far it is from here to here. So when you change this value, you make your graph taller. Make sense? And if we wanted to, we could continue and come over here and do another period. So we'll go through another cycle.
When we draw it and we only do like that, do you want us to put like arrows on the end, or?
It doesn't. I used to be like really picky about that, but your book doesn't do it, so I hate to be picky if your book doesn't. But technically, you are correct. It does continue. So to be truly technical, we should put those on, but your book doesn't, so I finally just got over it. Okay, let's pause right there. Well, no, we don't really need to pause. Are you guys all caught up?
Mm-hmm.
Okay.
So
We're good.
the A value controls
How tall it is. Yeah, how far from the midline it stretches.
Okay.
Okay, now if A is positive, like it is right now, it'll go up first. But if I change that to a negative, it would come down
Go
first.
down
And then
first.
up. Yeah, so you can like actually do different things to make it behave the way you want.
Okay.
Does this graph have any symmetry?
Sure.
Yeah.
I mean,
Does anybody recognize what kind of symmetry that is? They all have symmetry, all 6 of them.
Well, like, it's just
It's not y-axis, because y-axis I could fold it in half.
Is it rotational symmetry?
It does have that, but in terms of algebra, we usually say that it has origin symmetry.
Okay.
Because every point that's on there, the opposite point is on there. So pi over 2, comma 2, negative pi over 2, comma negative 2. If opposite points are on there, then it's called origin symmetry. Whereas the cosine graph we looked at earlier, it had y-axis symmetry. Here's a graph. It shows the original parent function dotted, and then it shows y equals 2 sine x graphed on the same place. And you can see that the intercepts are the same, but that the crests and troughs, are, is that the right word? That sounded strange. Crests and troughs are like taller. Make sense? Okay, great. Okay, so now we want to look at y equals sine of 2x. Our amplitude has gone back to what?
Uno.
Absolute value of 1 is 1. But our period is different.
Our period is pi.
Our period is 2 pi over 2, because b is 2, which reduces to just pi. We've actually shortened our period by half. So putting a 2 there actually makes the period shorter, not bigger. So we start at 0 still, but this time, instead of going all the way to 2 pi, we're going to stop our table at pi. And then we're going to go in by halves. So this is half pi. This is a quarter of pi. And what will that be?
3 pi over 4.
3 pi over 4, yeah, 3/4 of pi. Because we're going up by 1/4 each time. Look, that's 1/4, 2/4, 3/4, 4/4. So if you need to, you can count it that way.
And it's always 5, right?
Yeah, well, you could put as many as you wanted. I mean, there's no set magical number.
That's just how many points
I
you
just decided to because I wanted to make them hit the quadrantals, and I think it's easier for students if they hit the quadrantals.
And
So that's why I recommend doing 5. But different people do it different ways. Okay, so now let's plug in 0. If I say y equals sine of 2 times 0, so that's still asking me to find the sine of,
0.
and the sine of 0 is
0.
it is indeed 0. Then if I want to find pi over 4, sine of 2 times pi over 4. Well, check this out. And this is why it always goes back to the quadrantals. The way we have devised it, what does the inside clean up to? 2 pi over 4, which is pi over 2, right? Which is a quadrantal. And so that will always happen if you have set your table up properly. If you set your table up the right way, then that'll happen. So that's going to be what?
0, 1.
That's the 0.01, so that's 1. And then once you get there, you can fill it in without having to evaluate the rest. Every other one is 0, and if this one is positive 1, then this one is negative 1. So really, you only have to fill in the first 2. And then you just graph it. Okay, if I still let this be 2 pi, just to kind of give you an idea here of what happens on this graph. If now my period is really small, so it's going to wave up and down a lot faster. So this is half pi, that's a quarter of pi, and that's 3/4. Okay? So it still goes through 0, 0. No, yes it does. I had a weird moment. Pi over 4, comma 1, pi over 2, comma 0. I didn't do a very good job there. I shall fix it. Oh man, failure today. My goodness. All right, I'm better now, guys. Okay, let's try this again. Should be about right there. And then halfway between here and then back to here. So you can see how it's kind of squished together because it shortened the period?
Yes.
And if I wanted to continue out to 2 pi, if I wanted to do a second period over this way instead of going into the negatives, I could do that. Cut it in half again and then just keep extending it. So it would go up, it would come back down, it would go down, and it would come back up. So you can see you can fit twice as much in there, twice as many crests and troughs than we could when the period was too high. Make sense?
Yes, ma'am.
Okay. Anybody need to ask anything about this graph? Okay, let's pause for a second. So here what we have drawn, the dotted one is the parent function, y equals sine x, and the solid one is y equals sine of 2x. So you can see that you can fit twice as many crests and troughs in the same amount of space.